For this very basic case, see how we're using the parameter s. Remember that parameter s from chapter 14, the arc length parameter? So that's because we're integrating over an arc length. So the more proper way is to explain a line integral rather than integrating over an interval. That's the single integral, or integrating over an area, that's a double integral, and integrating over a solid, that's the triple integral. Here, yes, even though we are in space, we're not calculating volume, we're not calculating, well, we can calculate mass in one for one case, but the thing is we're integrating over a distance s, the arc length parameter. But again, think about that arc length parameter. You might remember it was not an easy problem to obtain because for the most part we will be given functions of t, because that's the easiest way to see a vector valued function, the parameter t, which is the position of a particle at different times, right? But in this case, for a line integral which uses the arc length parameter, that again is not always easy to parameterize, we will have to rearrange this integral. That is, this is the integral in the s parameter, and that's the new integral in the t parameter. I'm going to show you how do we get, that's the derivation proof, so to speak. So number one, again, the arc length parameter s of t, that's the integral from thank you. So that's the integral from 0 to t of, what was that? The magnitude of r prime of u. Remember how we changed the variable to u, and then we integrated between 0 and t? Okay. But what are we going to do here? Okay, how about we take the derivative on both sides for this? Think of this as an equation and take the derivative on both sides. Okay, ds dt, that's simply ds dt. Okay, right? ds dt. But what about the right-hand side? Do you guys remember this second fundamental theorem? That's the derivative of an integral, right? So integrate this madness here with respect to u, whatever it is, upper limit minus lower limit, that's going to be a function of t. Or simply go about the magnitude of r of t, dt, well, just r of t. Okay, I'm going to solve for ds right here for this new equation. What is this going to be? Okay, this will be ds equals to the magnitude of r of t, over r prime of t rather, times dt. Do you see this r prime of t dt right there? All right. So that's how I am replacing this ds with r prime of t. But what about this x and y in terms of x? We no longer write this in terms of x. So this time we will write this in terms of t. All right? And it's going to be a lot easier to evaluate a line integral with the parameter t, rather than having to find the arc length parameter and then on top of that potentially evaluate an even more complicated integral, which that's definitely not fun. All right, so that's how we that's how we evaluate, or rather we represent a line integral in the plane, but of course we can represent this in space. All we do is simply consider a function of 3 variables and consider the vector valued function in 3 variables, x, y, and t, which at the same time they will all depend on t. All right, and guess what? Okay, what if f of x, y z equals to 1? Remember how in a double integral, if our f of x, y is simply a 1, that gives us the area of the plane region, and on a triple integral, if the integrand is a 1, that gives us the volume of the solid. Well, so in this case, rather than getting the area under the fence for or projected by this curve in space, well, so this is going to take us back to the arc length because, again, are we not integrating over some length, over some arc length? All right? And, well, So what is this anyway? If this guy equals to 1, that's simply the integral from a to b of r prime of t, the magnitude of r prime of t dt. But what is the magnitude of r prime? Isn't that the integral from a to b of the square root of x prime squared plus y prime squared plus z prime squared? Isn't that the arc length integral, right? So if the integrand is 1, we're finding the arc length. If it's something other than 1, we're evaluating a type 1 line integral, which represents the area formed by the area of the fence projected by the curve in space. All right? Okay, let's get into some of those examples. All right, next page. Evaluate the line integral 1 plus x y squared ds given by, where c is given by the vector value function. T in the direction of I, 2t in the direction of j, within the intervals 0 and 1. For the most part, you guys will be given these limits of integration, or at least some information for us to get those limits of integration in terms of t. You'll see as we progress through the examples. All right, so number 1. Interesting, because this is a ds, I need to replace this into a dt. What do we need to do? Because ds will be now the magnitude of the derivative of the vector valued function. So number 1, r prime of t, what's the derivative of this vector valued function? The derivative of t, come on, that's 1. The derivative of 2t, that's 2. Okay? So I'm going to take the magnitude of this vector, that is the square root of 1 squared plus 2 squared, which equals the square root of 5. All right, what else do I need? I think that's about it. And we're ready to evaluate the line integral, the integral over the contour C, or over the curve C, that is of 1 plus x y squared ds. Oh, careful, because number 1, since we are no longer working with the arc length parameter, with the s parameter, we're back to the t parameter, the time parameter. That'll be the integral along the curve C of the same function 1 plus x squared plus y squared. I'm going to replace ds with the magnitude of r prime of t dt. All right, and now everything will be in terms of t, easier to work with. I mean, what's the price we have to pay for working with the t parameter? Taking the derivative of the given vector valued function and finding its magnitude. That's cheap, right?
Is that supposed to be x squared plus
Times, yes. I don't know where did that come from. Thank you. That's x y squared. Yep. So that's really cheap, right? And rather than parameterizing the s parameter, no, you don't want to do that. No. Okay, so we're good to go. Well, let me highlight this just to make it resonate to what we just did. Okay, so highlight the x component, y component, y component. As easy as substituting. And we have the limits of integration, 0 to 1. That's the integral from 0 to 1 of 1 plus x, which is t, times y, which is, careful, 2t quantity squared. And what's the magnitude of r prime? That's the square root of 5 dt. All right? Actually, guys, do you see how we are essentially doing a change of variables from the world of S back to the world of T? Doesn't that sound like the Jacobian, right? So really this magnitude of r prime of t is like finding the Jacobian to go from the world of s back to the world of t. If you can think of it in terms of the Jacobian, but in this case we're not computing the determinant of a 2 by 2 matrix. It's just one single factor. So that is the compensation factor to go back from the world of s to the world of t. All right? Okay, that's the integral from 0 to 1. That's 1. Okay, careful. 2t squared, that's 4t squared times t. Is that 4t cubed dt? And well, the result of this integral, wait, times root of 5 dt. And well, this is a very simple integral. I'm pretty sure you guys would get this result. 2 root of 5, right? 2 root of 5. Let's have a look at another example. But now see how the next example, it's giving us the information in a slightly different way. Well, so this is like the best case scenario. You're given a function of r, you're given the limits of integration in terms of t, and well, whatever the integral is, it doesn't matter. All we need to do is the substitution. All right. Example number 5, that's our second integral in terms of t. Okay, so evaluate the integral xy plus z cubed from the point 1, 0, 0 to the point negative 1, 0, pi along the helix c that is represented by the parametric equations x equals cosine, y sine, z. Do you remember the helix we did in GeoGebra? Right? So let's see if we can represent it. Okay, let me open a new GeoGebra here. Don't save, and open a new one. Okay, let me use the 3D graphics. Let me open the curve parameter. Okay, so curve, expression. Oh, come on, there you go. So that is cosine, right? Cosine t, sine t, t. The parameter is t, and I'm going to go from, what is that? 0 and pi, right? 0 and pi. There we go. That's the part of the helix. Only, well, if we see it on the xy plane, that's just half of the rotation, right? That's because it's only going between 0 and pi. But in 3D, it looks like this. Okay, I would like to plot the points just so you can see what we're doing. So, what is it? 1, 0, 0. And negative 1, 0 pi, right? Negative 1, 0 pi. Yeah, just to make sure we're actually, yeah, that's what it is. So essentially, with this integral, with this line integral, we would be finding the area of the fence projected by this curve in space. All right, that's what it is. Okay. All right, let's see. What about it? Okay. What do we need? Okay, r prime. So r prime. Well, let me write r first of all because this is given in parametric form. R of t equals to cosine t, sine t, t, and r prime equals negative sine, cosine, and 1. Careful, the derivatives, it's the derivative. Now we need to find the magnitude. Right, let's find the magnitude, that is the square root of negative sine squared plus cosine squared plus 1 squared. Well, sine squared plus cosine squared, isn't that 1? Plus the 1 squared, which is also 1, isn't that equal to the square root of 2? Right? So I believe we have everything we need. Okay? So the integral along c of x, y plus z cubed ds. Okay. Well, in rather than integrating with respect x, with respect s, we will integrate with respect t. However, we need a compensation factor. That's the element of arc length. That is the magnitude of r prime of t dt. Okay. Let's write down the integral. And again, let me highlight the cosine. That's our x. The sine. That's our y. And lastly, the z is the t right here. And let me use a different color, maybe blue. Okay, maybe this blue right here to represent this right there. All right, so this will be the integral from 0 to pi. That's x, which equals, what's that, cosine t sine t plus t cubed, that's t cubed, not yet dt, times the square root of 2 dt. All right, let's evaluate this integral. So this one I'm going to evaluate, so not like the other one, I just gave you the result. So okay, the integral of cosine sine, you can do it in two different ways, right? You can either set u equals to cosine, the derivative would be negative sine, but in this case you would need to compensate with a negative sign, right? How about instead make u equals to sine, du would be cosine, which is already there. That would be simply sine squared t over 2 plus t to the fourth over 4, but don't forget to multiply everything by the square root of 2, which is this factor there, and evaluate this between, what's that, 0 to pi, okay? And let's do upper limit minus lower limit. Okay, square root of 2 times, okay, upper limit, that is sine pi squared over 2 plus pi over 4, pi to the fourth over 4, okay, minus, do you agree that if we substitute the lower limit of 0 to those two terms, that's going to get all zeros? Minus big 0, okay? Okay, what is sine pi? Is that negative 1? Sine pi? No, 0, right? Okay, so this term is going to go to 0. That's going to leave us with root of 2, pi to the fourth, root of 2 over 4. Final answer. All right? Final answer. Alright, let's have a look at the next example. We're going to do a bunch of line integral examples because pretty much every example has different wording. The information that we're provided is going to be a little different, and we may need to take different approaches before actually getting the information we need to set up the line integral. Alright, the next example, example number 6. Evaluate the line integral x squared plus y squared where c is the path traveling counterclockwise around the circle x squared plus y squared equals to 4 from the point 2, 0 to the point 0, 2. Okay, here is where the direction matters because, again, let me go back to the first page. Remember when we reviewed how to parameterize curves? So we parameterized this circle of radius 5. But we didn't have any additional conditions. They just said parameterize this circle of radius 5. But they didn't say anything about oriented counterclockwise or oriented clockwise. So that's why I wrote both parameters. We came up with both parameterizations. In this case, they're being very specific. They're being specific about the counterclockwise orientation. So when it comes to parameterize the circle, R of t will be cosine t sine t. What am I missing here? The 2's, right? Because it's a circle of radius 2, and it's going from the point 2, 0 to the point 0, 2. Is that the entire circle? What part of the circle is this? It's just the first quadrant, right? Quarter of a circle. Let's plot that, right? And we're going to use that information to easily see the limits of integration. All right? So that is 2, 1, 1, 2. All right? So, okay, let's worry about the limits of integration in a second. Okay, so let's find the derivative r prime. That is negative 2 sine t to cosine t, and find its magnitude. Find the magnitude of r prime. That is the square root of negative 2 sine t squared plus 2 cosine t squared. So that'll be what? That's 4 sine squared t plus 4 cosine squared t. And we'll factor out 4. Why not? Let's factor out the 4. And you know this identity, right? Sine squared plus cosine squared. That equals to 1. 1 times 4 equals to 4. The square root of 4 equals to 2. So we're ready to set up the line integral. Alright, so that is the integral along the path C of x squared plus y squared ds. Okay, let's change this integral in terms of s to that of terms of t. That's the multiplying by the magnitude of r prime of t times dt. Okay? And well, what's x squared, what's y squared? Come on, this one is going to be a really simple one because it's going to take us back to that Pythagorean identity. Okay, this is x, and this is y. Just substitute where they correspond. Okay, and well, okay, that's let me use a different color for r prime. That's going to be these two right there. All right. Okay, so that's the integral of x squared, that is 2 cosine t squared plus 2 sine t squared times the magnitude of the derivative of the vector valued function, which happens to be what? 2 dt. Now, what are the limits of integration? Well, in this case, we are integrating over a circular trajectory. And well, since we are only looking at the part of the circle that goes in from those two given points, that's only the first quadrant. What are the limits? 0 to pi over 2. Okay, so what is that going to give us? Number one, the integral from 0 to pi halves, pi over 2, of 4 cosine squared t plus 4 sine squared t times 2 dt. Okay, how about we factor out the 4? That's going to leave us with, what's that? Cosine squared plus sine squared. Isn't that equal to 1? 1 times 4? 4. So this guy, all this is equal to 4. Okay, 4 times 2, that's the integral of 8 dt from 0 to pi halves. That's 8t from 0 to pi over 2, which is 8 times pi over 2 minus 0, that is 8 over 2, equals to 4 pi. All right? Okay. Let's look at one more type 1 line integrals. Okay, evaluate the line integral of x squared plus 2y minus z ds, where z is the line segment from the origin to the point 1, 4, 2. That's it. That's all they're giving us, right? So they're giving us 2 points, which is good. They're also being very specific that to go from that point, from the origin to 1, 4, 2, we need to go as a line segment. That means we need to come up with the parametric equations of a line, all right, with a vector valued function that describes a line. So number one, we need, let's call this A, let's call this B. So AB will be terminal minus initial, terminal minus initial. The initial is 0, so it's just going to be 1, 4, 2. All right. Okay, so let's write the vector valued function that describes. Oh, but on top of that, they're not giving us the limits of integration in like the other examples, right? But okay, if we parameterize, check. If we parameterize this line like this, okay, the initial, the x naught, y naught, z naught, they're all zeros. I'm not gonna write those zeros. This is simply going to be what? T, 4t, and 2t. However, when we parameterize a line segment from point A to point B, what are the limits for 0 to 1? So we have all the information we need. Well, almost, right? Let's take the derivative r prime. Take the derivative r prime. That equals 1, 4, 2. Oh, wait, yes, and then let's find the magnitude. Magnitude of r prime. That equals the square root of 1 squared plus 4 squared plus 2 squared. Okay, that's 1 plus 16, that's 17. 17 plus 4, is that 21? 21, the square root of 21. All right, so that's going to be our compensation factor to go from the world of S to the world of T. We have everything we need. Let's just evaluate the integral. Okay, so that is the integral along the trajectory C of x squared plus 2y minus z ds. But again, you need to go to the world of T. C, along C, x squared plus 2y plus, or rather minus, z, magnitude of r prime, dt. I will keep highlighting this. I mean, why not? So, x with x, y with y, and what was the other? Okay, I used this one. Z with z. And I'm going to use blue for the magnitude of the derivative of the vector valued function. Alright? Substitute. We got the limit. We got everything we need. Let's just go for it. Alright. That is the integral from 0 to 1 of, what's that? T squared plus 2 times 4t minus z, which is 2t, times the square root of 21 dt. Okay, let's simplify this because, yeah, there's like terms. Okay, so t to the second power, that'll be, okay, number 1, the integral from 0 to 1, t squared plus, okay, that's 2 times 4, which is 8. 8 minus 2, is that 6? So that'll be 6t times the square root of 21 dt. This one I'm not going to evaluate. I'm going to give you the result. That's equal to 10 root of 21 over 3. Right. Final answer. So that's about a few examples of type 1 line integrals. Let's move on to type 2 line integrals and what do they represent. Okay, so now we're going to integrate over vector fields. But what are we going to calculate? Well, number 1, let me go to the bottom of the page. This is how we're going to evaluate this integral. So we're going to have a force field or a vector field involved. And this time we may get different results. Actually, the results for type 1 integrals are typically positive results because again that represents the area of the fence, right? Under the or projected by the curve in space. But the thing here is this this type 2 line integral will represent something else. This is going to be applied into physics more often to calculate the work done by a force along a distance, which we already did, right? I mean, we already did that vector. Remember that vector projection? Remember that example when I pushed the chair with all my force, the force horizontally versus just a portion of my force by pushing it with an angle, right? So that's going to come back here. Okay. So again, this is the force vector. This is the distance vector. And well, there's some angle in between. Unless we're pushing an object in the same direction as the distance, that's just the multiplication of the two numbers. But otherwise, the actual work will be simply a projection, a shadow of the force onto the distance vector, right? Just a portion of it, not the full potential. What does that have anything to do with our situation here? And how is that related with the with the integral and all that? Well, okay, let's have a look at this picture on the right side, on the almost bottom right of the page. So we have this trajectory given by r of t. That is the c trajectory along we're going to evaluate the integral. That is the trajectory of an object, a rocket, a car, an airplane, whatever you want, traveling from point A to point B. Well, this time we're going to have some force, some driving force. Remember when we first described these vector fields, what they are, what do they do on objects in our world, in our universe? Well, so again, if we have a particle going from point A to B, that force field may help that particle move faster or struggle into moving, like the streamlines, like the going against the current, going with the current on a boat, or going what was that, against the wind, with the wind when we travel by airplane. It's the same situation. So, and in this case, we will be finding the work done by the force into moving that particle. So that's what we're going to calculate here, and it could be positive or negative depending on the direction it's going. Okay, so let's derive this. Number one, again, this force, it's going to be acting in the direction of the unit tangent vector. Why is that? Because the unit tangent vector, doesn't that go in the direction of motion, in the direction of the velocity, right? So, and that's what we want to know. For instance, right here we have this situation where, in this case, this force, the shadow of this vector in blue here, that's what the work of the force field is doing onto moving that particle along the direction. We can repeat that over here, for instance. We can repeat that here. So that would be this shadow only, maybe there, but that would be only this shadow only. So, and then what are we going to do? Guess what? Add infinitely many of those as a Riemann sum. Infinitely many of those works as a Riemann sum. That's going to be what? Isn't that the integral? So that's why we're evaluating a line integral that represents the work done by the force field. Okay, so what was that? Okay, the projection. So this is going to be the projection of the force onto the tangential. That is the dot product between F and T divided by the magnitude of T squared. That times what? Is that big T? Okay. But we can simplify we can simplify something here. We can simplify the denominator. That's because what's the magnitude of big T again? Right? That's because it's the unit tangent vector, right? So the magnitude is 1, right? So, boom, this goes to 1. Good. Okay, so that means this is equal to F dotted with T times T. Okay. So if we were to find the magnitude of this, okay, Find the because that's what we want to know, the magnitude of that projection. That's going to be the work done, right? That's what we want to know. And then add infinitely many of those magnitudes to get the total work to go from A to B, all right? So that's the magnitude of the projection of F onto T. Okay, find the magnitude of this. That's find the magnitude of F. Oops. T times T. All right. Okay. Let's talk about this. This quantity inside of the parentheses. Just focus on this. What is this? What would be the result of computing this? It's a scalar, right? Because the dot product between two vectors gives us a scalar, a number, all right? So let's use properties of magnitude here, if you will. So that's the magnitude of F. Come on. F dotted with T and the magnitude of T. All right? So in this case, well, again, what is the magnitude of T? 1, right? And what is the magnitude of F dotted with T? Isn't that just F dotted with T? That's all it is, right? F dotted with T. That's all it is. Okay? How is this going to be useful here? Well, that's because this time we are going to integrate. Remember 4 times distance? Okay? That's the integral along C of F dotted with T ds along the trajectory S. That's because the differential is S. That's for now it's the parameter S. We will change parameters later. Okay, what is this? Okay, what is F? Okay, F is simply F. Okay, that's given. Oh, how do we get big T? Remember how we get big T? Chapter 14. Not the arc length. So yeah, you're kind of close with the magnitudes and divided and all that.
R prime over magnitude of
R prime over its magnitude, right? So that's also given. R prime over its magnitude. Okay, oops, this is prime. And again, what is ds in the world of T? The magnitude, right? The magnitude of R prime, which is what we have been doing for the last, 10, 20 minutes or 30 minutes, times dt. Oh, look at this. Goodbye. So this is the power of line integrals type 2. You won't have to differentiate the vector value function. You won't have to go through finding its magnitude. Oh, yeah, no, you still have to differentiate. I'll take that back. So this is equal to, what's that? Oh, wait. That's the integral along C of F dotted with R prime of T dt. Right? Hey, isn't that what we have here? Yeah, it is. I know it looks different because this F, okay, this F right here is an F of x, y, z. But at the same time, given our vector value function, those x, y, and z are what? Functions of t. Right? Those are going to be our limits of integration. All right. We have plenty of time to go through one example at least. Okay. Oh, there's 2 examples actually. I think we're just going to do one maybe. The second one, it's going to take forever. Okay. Example number 8, which is our number 1 example for type 2 line integral. So find the work done by the force field. Okay, that's what we're finding, the work done by the force field in moving a particle along the quarter circle r of t cosine t sine t in the first quadrant. And well, they're literally giving us the limits of integration, 0 to 2 pi. And even if they didn't give us the limits, come on, the picture speaks by itself, right? It's very self-explanatory here. Okay, so, but I mean, the thing is, how are we going to evaluate this integral? Okay, Number one, what do we have? R of t, which is cosine t sine t. Okay? And take the derivative. Now check this out. I need to change notation for type 2 integrals. I know you guys are used to r prime of t, but for a big reason that you'll see, I'm gonna use Leibniz notation, dr dt rather than r prime. I'll show you in a second. Okay, that is negative sine t cosine t. And let's find the differential. That is solve for the r. Negative sine t cosine t dt. Okay. So we're given a force field. A force field given by f of x, big F of x, y, which is what? That's x squared. Negative xy, right? So, okay, because our line integral depends on t, we need to do a little bit of work with this force field, which is given as a function of two variables. We're going to reduce this two-variable function, or potentially a three-variable function, into one single variable function. That is, we're going to write all instances of x and y in terms of t's. How? Well, again, this is x, and this is y. Oops. All right. So this will be cosine squared t, comma, negative x, which is cosine t, sine t. But this will be no longer a big F function of xy now. This will be a function of t. All right? And I believe we have everything we need to evaluate the integral, to set up and then evaluate the integral. So in this case, since we're finding the work done by the force field into moving a particle along this trajectory, okay, before even setting up the integral, let's see if we can anticipate what we are going to obtain as a final result. Do you think we're gonna get a positive result or a negative result? What do you think?
Positive?
Why is it a negative result?
Well, because we have like a physical context.
All right. Okay, but how does that work to obtain a negative? Yeah, you're right. Yeah. I mean, even if we didn't have a physical context, we may get a positive or negative result. But I mean, how does that physical context play in the situation? Think about, where are we starting? Where do we end up? Where do we end up at? What is the force doing? The nature of the force here? Yes.
Moving against the force.
We're moving against the force because we're going from 0 to 2 pi, right? Come on. We're going in this direction, right? From 0, not to pi over 2. But do you see those arrows going against the direction of the particle? So that's how we can anticipate that we are going to get a negative result. Is that going to be the case? Well, let's see. So work W, that's the integral along C of the force dotted with the differential dr. All right? So we will no longer do the other type. This is going to be a different evaluation. Okay, so what is this going to be? Okay, this will be the integral from 0 to pi over 2, 0 to pi halves, of f. What's f? It's f in terms of t, what we just rewrote. That's cosine squared t, negative cosine t sine t, and dotted with the dr vector. Remember the dr vector is negative sine cosine dt. Negative sine t cosine t dt. Okay? Alright. Dot product this vector, okay, that is cosine squared times negative. Wait, I'm missing something. Oh, no, this is this is a comma here, right? Yeah. Got it. So this will be the integral from 0 to pi over 2. That is cosine squared times a negative sine. That is negative sine t cosine squared t plus, what's that? The product between negative cosine times sine times cosine, that's another minus, right? Another minus sine t cosine squared t dt. Okay, we have like terms in here. That is negative plus a negative, that's a negative 2, right? Let me write that negative 2 outside of the integral, and that is from 0 to pi over 2. What's that? Let me write cosine squared t sine t dt. How would we evaluate this integral? Yes.
Can we separate like we did in the previous example?
Separate it.
Like have cosine t times cosine t sine t?
Yes, okay, so cosine, sine. So we would have 3 factors here. That kind of make it a bit more complicated. It's a U substitution, right? Do we all agree that this is going to be a pretty basic U substitution? Well, so, okay, there's a U substitution going on. Final answer, negative 2/3 after doing the U substitution. Oh, isn't that a negative result? What we were expecting? Yes? Yes. Okay, so what's the difference between type 1 integrals and type 2 integrals? So for type 1 integrals, actually we didn't care at all about the orientation of the curve, right? Because we were not integrating over a force field for which that orientation may affect the nature of the result. That is, could be positive or could be negative. And in this case, since we are integrating over a trajectory field where there's a driving force that will affect the work done, well, so orientation of the curve will matter. So let's rework example A given the same situation. However, if we change the orientation of the curve, notice how we have sine t and cosine t as opposed to cosine then sine. That's how we change the orientation of the of the trajectory. But I'm not going to evaluate the whole thing. I mean, I think it's all we want to get out of this is that the integral along C of f dotted with dr, what should we get? Positive 2/3, right? 2/3. All right. Yep. Why not?
Because that reparameterized the circle, so it's going.
Exactly. So that now by interchanging the components of the vector values function or the parameterization of the quarter of the curve, now it's going to cause the following. The effect will be to go from this direction, that direction, right? In that direction. Do you see those arrows going in the direction of motion this time? So that's like having a tailwind, having the airplane go faster, or going with the current on a river, right? So that's going to favor the work. So the work will be positive this time. All right. Okay. No, I don't want to go through example number 10. That's going to be a good one to warm up next time, okay?